And good afternoon, morning, or evening, calculus people. This is day 9 in our integration unit, and we're going to be looking at part 2 of those areas under the curve. So we're going to look at two quadratics together at first, and then we're going to look at curves where they don't necessarily intersect, but you have some vertical line limits put on them, and finding those areas. And those are the two areas we'll look at today. And then once we're done that, I'll put up the practice for the next day as soon as we pop open the board here. Okay, so let's set up here. What are we going to look at today? Okay, so this is day 9. And this is the last unit, unit 6. We're not going to, I might put up a couple videos just for people that are going into university about sine, cosine, and tangent derivatives, but it won't be part of our final exam. Okay, as I mentioned last video as well, when the final exam comes, you can make your own cheat sheet up from a 8.5 by 11 paper with all your derivative formulas, all your integral formulas that you want on there. You have to make your own though, as that's part of your prep for it, I guess. So that's something that you'll need to do. What we're going to do today, though, is we're going to look at area between two quadratics. And then we're going to look at area under a curve and then we're with vertical limits. Oh, we'll say vertical lines rather than limits as endpoints. And that's the two type of examples we're going to look at this morning. Okay, so let's start by doing an example of the two quadratic ones. It's exactly the same as we were doing with the line and the quadratic ones. We use the fundamental theorem of calculus to find that area. So let's prep an example. I might even use a little bit of Desmos to show us the graph of it as well to help us out a little bit. So let's say, let me just get my preview up here so I can follow my timing. Okay, there we are. Okay, so let's do this example here. Let's say that this is two quadratics example. So we're going to go with, let's go with y equals x squared plus 3x plus 2. Okay, let's get that squared in there. Okay, and then let's go with y equals negative x squared. So that's when it's going to open down. So the one opens up and one opens down, so they'll close into each other. Negative x squared, what do I got here? Plus 5x plus 6. Okay. Put that in there. So again, come on, there we go. Okay, so there's our two quadratics. So which one is the upper one? Which one's the lower one? Probably the upper one's going to be the one that's bending down, the negative one. And then this one's probably going to be the lower one, but we're not sure 100%. So the first thing we want to do is first let's calculate the intersection points. Okay, that's our first step as always. So we're going to take these two quadratics. I guess we should put the question in there, huh? Find the area between these two curves. There we are. Okay, so here's our example. Let's go ahead and let's find those two intersection points. So this is going to equal the other one. Okay, so let's take our marker out here. Okay, so x squared plus 3x plus 2 will equal negative x squared plus 5x plus 6. So we have to make a quadratic out of this. So I'm going to bring everything to the left. So I'm going to add an x squared, subtract a 5x, and subtract a 6. On both sides. So this is going to become 0 when we eliminate all of those. X squared and x squared is 2x squared. 3x minus 5x is negative 2x. And this would be negative 4. Okay, so this is factorable, so we can take a common factor out. Okay, divide the 2 out on both sides. Okay, when you divide 0 by 2, it's still 0, so that doesn't change anything. Factor it. Okay, x minus 2 times x plus 1. Okay, adds to negative 1, multiplies to negative 2. So that means x is equal to 2 and x is equal to negative 1. So negative 1 and 2 are our two intersection points. So we can do a little sketch of it. More than likely, it's going to be, okay, we're going to have the curve and then it intersects at plus 2. We could actually figure out what it is. If we put a 2 in here, it'd be 4 plus 6 plus 2, right? So it'd be up near 12. So this, we have the one curve like that. Actually, this is not a great diagram. Let's do a better diagram here. Okay, so you're going to end up having kind of one like this. And then one like this. Right, and this is, I don't know, this one here, where if it's on the, where it is, but this is a negative 1. So negative 1 would have gave us 1 minus 3 plus 2. So it's right on the 0 line, so it should be up there. And this one here would be 2. Okay, if you're not entirely sure, so this would be the negative x squared plus 5x plus 6. And this one here would be the other one, x squared plus 3x plus 2. Little trick here, if you're not entirely sure and you're working on, and you can just whip out Desmos. So you could go and type in on Google Desmos. So bring it over here. Okay, the graphing calculator, and you could just plug those 2 in. So click this. Okay, wait till it loads up. And you could just double check to make sure. So it was, our two equations are x squared. So x, shift the little hat symbol above the 6 on the keyboard. Okay, 2 plus 3x. So there, that's probably going to be our lower limit there. So there's that one. And then in a different color, we'll do the negative one. Negative x squared. Okay, plus 5x. Plus 6. Okay, handy dandy. Okay, so there we can see, if I bring up Desmos here, okay, it was not exactly like my diagram, but basically you can see, if we zoom this out a little so we can see it here. Shift this down a little bit. Okay, so you can see that the intersection point indeed is at negative 1 there. Okay, well, negative 1 and 0. That's one intersection point. And we can see the other intersection point is 2 and 12 right there. Okay, we could have figured that out manually, but Desmos makes it look. So we want this area in here. So the upper curve is the blue curve. So the upper curve is the negative one, and the lower curve is the positive one, right? The red one is the lower curve. The upper one is the blue one. So let's work that out. Okay, let's get this out of our way here. Okay, so in fact, we labeled it correctly here, even though it doesn't look, it's just a sketch, like the axis lines, shouldn't even bother putting the axis lines in there really. Okay, so now we got to use the fundamental theorem of calculus. Okay, so once we've got the intersection points, the second step is then to write out the fundamental theorem of calculus for the area. Okay, so let's go ahead and do that right underneath here. Okay, so area equals, let me get my marker back here. Okay, so area equals, okay, we've got to go from 2 on top down to negative 1. So 2 is the rightmost point. Okay, those were our 2 intersection points. The first one was negative x squared plus 5x plus 6. Okay, that's the upper limit. That's the top curve. Subtracting the bottom curve. So the bottom curve was x squared plus 3x plus 2. Okay, put it in brackets like that, and this is the whole thing, dx. Okay, so that's so what we have to do is we have to take this and subtract this. So this is going to change the signs in all of these, and then we're going to add them together. So we'll do it step by step here. So this would be negative x squared plus 5x plus 6 minus x squared minus 3x minus 2 dx. Okay, then we can combine the two negative x squared, so that's negative 2x squared. 5x minus 3x is 2x. Okay, and 6 minus 2 is 4. Okay, so there is our equation that we are going to integrate now to get in our next step, we integrate this equation to find out what the area under that curve, or between the two curves, pardon me. Okay, so using integration skills, let me move this down a little bit. Not that far. Okay, so integrating. Okay, so we remove this integration sign and do the integration. So the area is going to be, all right, so negative 2 x cubed divided by 3, okay, plus 2 x squared divided by 2, plus 4x divided by 1, okay, plus a c. Okay, since we're doing definite integral, we can cancel the c out. Okay, we can simplify this simply. Negative 2/3 x cubed plus x squared plus 4x. Okay, so now what we have to do is we have to plug in the number 2 and then subtract the number negative 1. Sorry, I was going to say 1 there, but negative 1. Okay. Okay, let me just set up my example here, and we'll work that out. Okay, I need more space. There we go. Okay, so here we go. Okay, so we're going to plug in negative 2/3, 2 cubed plus 2 squared plus 4 times 2. Okay, that's going to be that side. Minus negative 2/3 times negative 1 cubed plus negative 1 squared plus 4 times negative 1. Okay, so we got our variable plugged in. Do some work here. So this will be 8 times negative 2 is negative 16 over 3 plus 4 plus 8 minus negative 1 times negative 2/3 is a positive 2/3. Negative 1 times negative 1 is positive 1 minus 4. Okay, got to do a little bit of crunching of the numbers. Okay, so this is going to be 12. So this will be negative 16 over 3. This will be 12. 12 over 3. 12 times 3 is 36. So this will be 36 over 3 minus, okay, this is going to be 1 2/3 minus, so we'll keep the 2/3 here, minus 3, which is 9/3. Okay, keeping on. This is 20 over 3 minus negative 7 over 3. So this is going to give us a positive there. So this is 27 over 3, which equals 9. So our answer is 9 square units. Okay, and that's an example of still using the same technique that we used before, but having two quadratics. So what the technique is, that's a long one. Okay, technique is to find the two intersection points by equaling them together. Okay, this one we ended up having to factor quadratic. Writing out the fundamental theorem of calculus, or the area formula, which is the upper curve minus the lower curve, integrated from the right intersection point to the left intersection point. Okay, we've got that written here. We simplified it, then we integrate to get the area under the curve. Then we are doing a definite integral, so we plug our numbers in to get our square units in between the two curves. Okay, similar. Okay, so that's our first example. That takes us about 18 minutes or so. So we'll get in our second type of example I wanted to look at today, and that is what happens when we get an example where we're just looking at area under the curve and we're just given two vertical lines. Okay, so let's take a look at an example like that. This will be our next example. So I'll title it up. Okay, let me pop one up on my other page here that will be, let's say, medium type quality, not too hard, not too easy kind of thing. Let's see if I can find a decent one here. That one's fairly easy. And that one's pretty hard. Let's do the fairly easy one first. If we have time, we'll do the other one. Okay, so this is an example of finding the area under a curve between and two vertical lines. We'll say endpoints. Okay, so let's say find the area under the curve y equals 3x squared. We'll go plus 2. We'll make it real simple. and the x-axis from -2 to 2. Okay, so they're giving you the two limits here, and they're giving you the curve. I should maybe make the curve a little bit harder than that. No, that's good. We'll keep it that way. Come on, there we go. Okay, so let's do a little bit of a sketch here. So what we have is we've got this quadratic equation here. Zero, when you put a 0 in for x, 2 becomes y. So it kind of looks like this. And then we want -2 is here. +2 is there. So if you can't sketch it out, or you're a poor grapher and you're not, you don't like quadratics and stuff, you can always, get that Desmos out that we used last time, this thing right here. Okay, we can go, okay, well, let's see what it would look like here. Let's see if I put in y equals 3x squared plus 2. Okay, so there it is. In fact, it does go up on 0, 2 there. So, and then if we put in the two vertical lines, okay, the vertical lines would be x equals -2 and x equals +2. Okay, so this is what, and the x-axis is here. So we're trying to find the area right here. Right in here. Just to there. Not this stuff down here, but just to the x-axis. Okay, so we've got a pretty good sketch of it there. So we're pretty close. We're good. Okay, get this out of our way here. Okay, there's our sketch. This is 0, 2 here. Okay, so what we have to do then is we don't have to worry about finding the intersection points, because we know that the intersection point is at -2 and 2 for x. So what we do is we just use the fundamental theorem of calculus. We go, the area will equal from 2 to -2, okay, rightmost to leftmost, the equation 3x squared plus 2 dx. Okay, and this is even simpler than what we did before, because we just have this one curve to worry about, right? So we don't have to do any combining. We just go straight into integrating. So if you integrate this, you're going to get 3x cubed divided by 3 plus 2x divided by 1 plus c. C's will cancel out. We'll go from 2 to -2. Okay, that's going to cancel down to x cubed plus 2x. So we just plug in our values, 2 and -2, to get this area in here. Okay. X cubed, or I don't need x cubed. Pardon me, 2x cubed, or 2 cubed, finally got it right. 2 cubed for the x cubed plus 2 times 2 minus, okay, this is where we need -2 cubed plus 2 times -2. Okay, so this is 8 plus 4 minus -8 minus 4. 12 minus -12, and we get an answer here of 24. Units squared. Okay, pretty easy, that one. Okay, let's check our time here. It's about 25 minutes. So let's sneak one more in, 2 curves, and then tomorrow I'll give you the practice sheet with this and the solutions. Okay, so this one we're going to do area between 2 curves and 2 vertical lines. So we're going to combine the 2 that we just did. Okay, so what we do here is we got to get our examples. So let me pull one up here. I got one here that's not too bad. Let's see what we got here. Okay, so let's say we have y. Find the area between the curves. Y equals x squared minus 4x, and y equals x squared minus 2x. From 1 to 3. From x, I should put in there x equal 1 to x equal 3. Shouldn't assume that you guys know that it's x's. Okay, so let's just put those squares in there. So to help ourselves out, we could do a little sketch. I'm going to use Desmos because it speeds things up for us. So, you know, back in the old days, we had to use a graphing calculator, but now if you got a Chromebook around or a phone, you can just go on Desmos. Okay, so what is that going to look like if we put those 2 curves in? Okay, x squared minus 4x. Okay, we're going to change our window a little bit. Okay, and x squared minus 2x. Okay, and x equal 1. It's getting pretty conglomerated there. X equal 3. So let's bring this up so we can see it a little better. Okay, so we basically want to find this area between the black curve and the green curve. So notice that the black curve is on top. X squared x squared minus 2x is the top or the upper limit. And the other curve is the lower limit. And you're like, well, it's below the x-axis. What's going to happen with the area? Well, this will end up being a negative area then, because that'll mean you'll be getting the area here, right? So we're going to do that calculation here and see what we get between these 2 curves. So let's get this out of our way. See if we can get this done in 10 minutes. Okay, and let's go ahead and do our calculation. So what we're going to be having to do is the upper limit was the x minus 2 curve, as we saw. X squared minus 2x, pardon me. So we're going to do an integration from 3 to 1, which is our vertical lines, of x squared minus 2x minus x squared minus 4x dx. Okay, so nicely for us, this cancels out here. X squared minus x squared is 0. Negative 2x minus negative 4x, 6x. Okay. Or sorry, what am I doing? Negative, I got to better do it correctly here. Let's simplify it here. So this gives us 0. Negative 2 plus 4x is 2x, not 6x. Plus 2x dx. So that's an easy integral for us to do. Okay, that's 2x squared divided by 2. Okay, and then that is from 3 to 1. Oops, sorry. Okay, and then we can simplify it a little bit. And the square units there, it's just going to be 3 squared minus 1 squared equals 8 square units. Okay, so that's pretty straightforward. And if we look at our Desmos example, it gives us a good idea. If we kind of count it out, we can, if I slide it over here, you know, and you're looking at it, you're like, okay, well, there's kind of a part there, there's one there, there's one there, there's one there, there's a part there, there's there, there's there, there's there. So it looks about like 8 square units. Looks good. Sorry, guys. Sorry about that. So that gets us to the end of our instructional part of area under the curve. So now we just need to do some practice. So that'll be for tomorrow. Is about a 30. We're into 33 minutes here already. So there's a couple more examples, 3 more examples to look at. So what I'm going to do is I'm going to stop the video here, and then for the next day, I'll post up some practice ones and then some solutions. Okay, and that closes the book on integrals. That's as far as we go with integrals, and that's as far as I'm going to go this year with testable calculus. So that means after today, okay, you'll do that practice one next day. The day after that, I'll have the hand in, okay, so day, I guess whatever day it is, 10 or whatever, will be the practice. Day 11 will be the hand in. Then day 12, I'll come up and put a video up with the outline for the quiz, send the quiz out. That'll be our last quiz, okay? And then the rest of the calculus that I'm going to put up, if I put up any videos, will be for the final exam. Okay, so that means we should be done beginning of June there. If you're following along with me, if you're a little bit behind, that's good. That's not good. It's okay because in the fact that you'll have lots of time to catch up there. And then I'll send out the exam for the integral unit, and I'll also send out about a week later the final exam. Okay, and I'll do a little spiel, a video on final exam, what you need to do, what you need to prepare, what you got to do coming as well. Okay, so I'll do all that coming in the next week or so. Okay, so good luck.